Я готов начать лекцию. Что мне нужно нажать, чтобы она началась? И это вы должны сделать. Ага, отлично. So this is the last lecture of the Topology 2 course. And its number is 10 in the booklet. And here I have also written 12 divided by 2, because part of today's lecture will be lecture 12 from the booklet, but only the first half, so I've divided 12 by 2. In order to follow today's lecture, you must have the material of the previous lecture at your fingertips. And so I will begin by very briefly repeating the main points of the previous lecture. So, last time, what did we do last time? Well, last time we defined the cohomology functor H star, which is a functor from the category of simplicial spaces to the category of graded abelian groups. And to construct this functor, we began by constructing the cochain complex for the functor, which is denoted by CK X G, and by definition, it's just the set of homomorphisms between the chain complex X G and the group G. Now here, X is a simplicial space, G is an abelian group, and we are considering the cochain complex whose elements are chains or just homomorphisms from, because elements are cochains, which are homomorphisms from the chain complex to the underlying group. And the next thing we must define in order to obtain a cochain complex is a boundary operator, or rather a co-boundary operator. Notice that the indices are up, and the co-boundary operator will be an operator from CK X G to CK minus 1 X G. I'll write the minus 1 in red to emphasize that, unlike the situation for the chain complex, where here you would have plus 1, we here have -1, so the arrows are reversed. And so how is the boundary operator defined? Well, it is dual to the co-boundary operator is dual to the boundary operator. And so it's defined in the only reasonable way that it can be defined. So to obtain dk of some cochain ck, we do the only thing that one can do in this situation. Namely, we take the pairing of ck, and what do we pair it with? Well, it has to be an element of ck minus 1. So we apply the boundary operator to some chain ck plus 1. We'll have a chain ck plus 1. We apply the boundary operator to it and take the pairing. And what we obtain is a number. So we have defined the co-boundary operator on a chain of ck plus 1. So let me write this in more detail. D k of ck is applied to some chain ck plus 1. So this is the definition of the co-boundary operator. It is easy to prove that if I do dk and then I do dk minus 1, then what I get is 0. This is very simple to prove. We just write out the definition. We apply dk and then dk minus 1 to some chain. And as we do that, first, after the first time, a boundary operator jumps out, and after the second time, a second boundary operator jumps out, and because of the Poincare lemma, dd is equal to 0. We get 0 here. So we can define the cohomology group H K C G in the usual way, namely as the kernel of delta K quotiented by the image of delta K, note minus one here. So we have obtained the mm, homology groups. And the next thing that we want to do, and I will not repeat this, is to see what happens when we have a simplicial map of one simplicial space to another, then we get an induced homomorphisms of the chains and eventually of the homology groups. And all this satisfies this. So the induced homomorphism is denoted by a star upstairs. And this functor is satisfies the properties 1, 2, 5 of Steenrod-Eilenberg. So that's the first thing that we learned last time. And now the next thing that we want to do is to define the cup product. So the cup product is an assignment of any pair of cochain groups to the cochain group C P plus Q X R. Now notice there's a hat on these C's. This has to do with the fact that we don't use oriented simplicial homology. We used ordered simplicial homology. I will not remind you what that is. We will eventually come to that a bit later. Now, how does one do that? Well, first of all, let me repeat that X is a finite simplicial space, and R, once and for all, and this will be true all day today, is an associative, commutative ring with the unit. So how does this work? Well, the definition is this. As many times today, the definition is in a sense the only possible one. So we have CP cup by C. Oh, I forgot the Q here. CQ. And this is assigned to a simplex V0 and so forth, V P plus Q. But this is not a simplex. This is a chain consisting of one simplex multiplied by +1, where 1 is the unit element in the ring R. So this is defined. So this must be a number. We're considering a pairing. This pairing here, and this number is defined in the only way that this can be done, namely, let's do this. So we take CP and we apply CP to the beginning of the simplex. So apply it to V0 and so forth, VP. Now, these are ordered simplices. And we obtain an element of our ring, and we multiply that by the other cochain Q applied to the simplex that begins with VP and ends with VP plus Q. So this is the definition for a chain consisting of one simplex. We extend this by linearity to any chain. And after that, from the chain level, we pass to the homology level, and we obtain a cohomology group, H. We take the sum of all the cohomology groups and we obtain a graded group. Supplied with a multiplication operation. So the gap product is a multiplication operation. It carries over to the homology level, and we obtain this object. And the main fact is that this is a graded ring. And this ring is skew commutative. Which means that if I multiply alpha P by beta Q, which are elements of the cohomology groups of dimension P and Q, and I inverse the order, then what I get is something with a sign. The sign is minus the P multiplied by Q. That is the second part of what we learned last time, and the final part at which we stopped is Poincare duality, and it is the following: we have a duality between H K M N R, where Mn is a connected, smooth, oriented manifold, and the cohomology group H n minus k Mn R which is obtained in a rather clever way, which I cannot describe in detail right now, but try to remember the picture that was on the board last time. It was a picture of a manifold with a triangulation, and with the dual cell structure, the dual CW complex of that triangulation. And so the homology, and there was a bijection between the simplices of the original triangulation and the cells of the how do I denote the cells? Sigma n minus k I. So this is the same I. There's a bijection in this I, like that. And using that bijection, we constructed this homomorphism by first on the chain level, we considered phi k, which is a map of C K M to C n minus k upstairs of M. And I put a little star here to stress that this is the manifold with the CW structure obtained here. And the rule for this map is this: to any K chain, CK, which can be written as the sum of AI of delta KI, where the delta KI are the original simplices of the triangulation of the manifold. And to this we assign a cochain n minus k, Cn minus k, which is given by the following formula, which again is the only reasonable one in the given context. So we, if we apply this cochain to a cell, C n minus k I, where Cn minus ki is the cell due to delta ki in this field. And then we get the coefficient ai. I explained that somewhat differently in the previous lecture. Instead of considering a chain with coefficients ai, I considered just one simplex here, and extended by linearity. Today it's more convenient for me to write it this way. So, okay, it has taken me half an hour to review the previous lecture, and now you're ready to try to understand the new material. And before I go into that, let me say that so far we have really done nothing new by dualizing to cohomology. What we have obtained are dual theorems, and of course the Poincare theorem, the Poincare duality, is an important and remarkable fact. It says that in a certain sense, the topology of a manifold is symmetric to the middle dimension, which is something that is really completely unexpected. Okay, so now we continue with the new material, and the first thing that we will consider is the CAP product. So the CAP product is denoted like this. And unfortunately, there are actually two CAP products. One is the homology-homology CAP product, and the other is the homology-cohomology CAP product. Standardly, the same notation is used for both, which is confusing. However, in this lecture, we'll only define the homology-cohomology CAP product, which we'll need further. So there will not be any confusion. So what is the CUP product? The CUP product will be defined on the chain level. As usual, it will eventually. So I'm having a problem with these. So we have a cochain, and we have a chain, and we want to compute their product. And well, let me write out what this does on the homology level immediately. So to any pair of elements of the cohomology groups of dimension P and Q, this product assigns, sorry, so this is a cohomology, homology gap product. Here you have a cohomology group, here you have a homology group of dimension P plus Q. And the result of this multiplication is an element of the homology group of dimension Q. And so how do we do this? Well, again, we do things in the only reasonable way. We have CP multiplied by a chain of dimension P plus Q. So instead of a chain of dimension C plus Q, I will consider a simplex, or more precisely, a chain with one, with a single non-zero element. So this here is a chain consisting of one simplex multiplied by the unit of the ring. R is still an associative commutative ring with unit. And so this is equal to what? Well, we do it whatever we can do. We take the pairing of CP with the beginning of the simplex. So it's V0 and so on to VP. And so what we get is a number. And then we leave V0 VQ. Sorry, VP, V plus Q. So this is a number, an element of the ring. This is a chain consisting of one simplex with coefficient 1. So it's when we'll move on to the homology level, then this will give us an element of the homology group HQ. Now there is a series of lemmas which follow from these definitions. The first lemma, so let me write it here. The first lemma is a kind of Leibniz rule. It says the following, that if I take the boundary of CP multiplied by CQ, CP plus Q, sorry, then what I get is the following. The first term will be CP multiplied by the boundary operator applied to CP plus Q, plus the other way around, the boundary up, wait a minute. The co-boundary operator applied to CP multiplied by CP plus Q, and this has a sign, and it's -1 to some power, which I can never remember. It is Q. There are two more lemmas. So the proof of this lemma is just you plug in the definitions and things work out. There are two more lemmas which I will not state here. You can read them in the booklet. And using these lemmas and this definition, we come to the following important theorem. H n minus k now we have moved away from a general case of simplicial spaces, and here we have a smooth oriented connected manifold. And this homology group is isomorphic to the homology group K M R and this is an isomorphism, and the isomorphism is called phi star. Oh no, I won't call it anything. It works like this. You take alpha n minus k. So this is an element of this cohomology group. And to this element, we assign, we're going to construct the this isomorphism from right to left. So we have an element alpha k, which is a cycle or an element of the homology group HK. And to that cycle, we assign the following no, sorry. No, I was right the first time. My mistake. So we go from left to right. We take a co-boundary, an element of the cohomology group, alpha n minus k. And to that, we assign the following element. We take alpha n minus k, and we take its cup product with the fundamental class. The fundamental class of the manifold. I had intended to give you the proof of this theorem, but I am doing very badly from the point of view of time. So what I will do is skip the proof. You can read it in the booklet. And when you do that, please pay attention to the fact there is a summation symbol missing in the key computation needed to prove this theorem. What one does, you see, we have already proved before that these two groups are isomorphic. So the main theorem is that this isomorphism is obtained in this way. Now, the advantage of this theorem over the previously proved theorem, in which we proved that this group is isomorphic to that group, is that this can be efficiently computed. Whereas the original proof of the theorem was based on a triangulation of the manifold, and it is in no way canonical. It is only, it depends on the choice of triangulation. Here we have a canonical isomorphism between these two groups. Now, the theorem that we proved in the last lecture, it sort of goes from right to left. We proved, we constructed a mapping from here to here in this direction. Now we're constructing the mapping in the other direction, and I prove of the theorem is based on analyzing what happens in the two cases, and shows that this assignment actually gives one of the isomorphisms from right to left. Okay, so now we pass to lecture 12, to its first half, and it is about vector bundles. What is a vector bundle? Well, a vector bundle is a fiber bundle whose fiber is k-dimensional linear space. However, I will state the complete definition of a vector bundle without appealing to the notion of fiber bundle, because fiber bundles were a long time ago, and you perhaps do not remember at this moment what a fiber bundle is. A vector bundle, so this is where we'll be talking about the category of vector bundles. So definition, what is a vector bundle? A vector bundle psi consists of a mapping P E to B with a fixed space called the fiber. Where B is paracompact. A paracompact means that it has in any covering of the space, we can inscribe a covering which is locally finite. The advantage of paracompact spaces is that for paracompact spaces, you have something called the partition of unity, which I'll explain a little later. So is paracompact and connected? Problems with these. So it's paracompact and connected. P is of course continuous and surjective. And F is n-dimensional vector space over R. And we have the following diagram. As usual, bundles are shown vertically. This is P. So if I take any point V, then this point must have a neighborhood U, such that if we take its pre-image under P, so here we have V of U. Then we stipulate that for any point B in B, there exists a neighborhood U such that its pre-image is homeomorphic to U cross F, where F is the n-dimensional vector space over R. And if we take this projection, the first projection to the first factor, then this diagram is commutative. So let me repeat this long definition. We are considering vector bundles. A vector bundle consists of a surjective map of a topological space on a paracompact space with a fixed fiber, where the fiber is the n-dimensional vector space. And it is a surjective map which makes this diagram commutative, makes it commute, and an important expression here is that this is a locally trivial bundle. So locally it behaves like a trivial bundle. So let me continue with this. The first thing that I want to mention here is the notion of pullback. So the pullback, denoted F star, is a map of a certain space E1 to B, we have the following situation. We have our bundle E, P, B, and we're given a map of some space X. And a pullback is the following construction. It's a vector bundle. Well, in the case of vector bundles, E1, this is denoted F star of P. Here we have a certain map, which I'll describe in a moment. And this is defined in the following way. E1 is, by definition, the set of elements B, E, where B comes from B and E comes from E. But they're not arbitrary elements. They are such that F of E must be equal to B. Intuitively speaking, we can say this, that we have a map of some space X to B. And then over any point of X, we actually place the fiber of the original bundle. The original bundle. So we're really pulling back the upstairs structure that we have on B over X. Let's see. I am, in a certain sense, running out of time, but I apologize, but I will take an extra 20 minutes to finish today's lecture. So I have defined the notion of pullback. After that, the next thing that I want to say is to define the morphism of two vector bundles. And what is that? Well, it's a square diagram E, B. Oh, sorry, I did not define this map here. So here, F star of P, this map here, is by definition just it does not depend on E. It's just on B. It's just F of P. Okay, so if you have two bundles, two vector bundles. A morphism is just a square diagram like this. Where these are continuous maps, and the diagram must commute. Two bundles are isomorphic if these I'm sorry, I forgot to say that both maps, capital Phi and Phi, are linear on the fibers. So the fibers are mapped to fibers linearly. So two vector bundles are isomorphic. If these maps are homeomorphisms, which are isomorphisms on the fibers. Okay. So let's consider some examples. First example is the trivial bundle. So it's V and R. To B. So the first projection, a trivial bundle. The second example is the tangent bundle of a manifold. And this is the most important example. The next example is the normal bundle of an embedded manifold. So if you have an embedded manifold in Euclidean space, then you have its normal bundle. And this gives you another example, important example of. And for today's lecture, the most important example will be the canonical Grassmannian. So the canonical Grassmann bundle. When we studied fiber bundles, one of the important examples was the Stiefel over Grassmann bundle. This is not the bundle that we're considering here. Here, we consider a bundle denoted gamma M K E M K to G M K. Now here, GMK is the set, K is less than M, is the set of K dimensional planes in M dimensional Euclidean space. So this looks like this. You have all the k-dimensional spaces here in R M. And EMK is the set of k-dimensional planes in m-dimensional Euclidean space, but each with a marked point. And the projection is the natural one to each plane with marked point. We assign the plane itself without the marked point. Obviously, this is a k-dimensional vector bundle because the fiber over any point of G and K is just a linear space of dimension K of all the points of this plane. Now, we will denote by gamma infinity K the bundle K, where this is the E infinite K or G infinite K are both inductive limits of these the spaces here, because there's an obvious inclusion of GMK into GM plus 1K, and similarly an inclusion of EMK into EM plus 1K. And if we pass to the inductive limit, we obtain this bundle where, in this case, we also have a k-dimensional vector bundle here. So this is the important object that we're going to use immediately to state the next very important results of this course, the last theorem in the last lecture of the course. This theorem says the following. Let us denote, so this is a classification theorem. Let us denote by V1 K over V the k-dimensional bundles over B. B will be paracompact and connected up to isomorphisms. And so the theorem says this. There is a one-to-one correspondence between vector bundles, or more precisely, isomorphism classes of vector bundles over a fixed base B, and the homotopy classes of maps of the base to the infinite dimensional Grassmannian. This is a very beautiful and powerful theorem, which classifies in terms of homotopy maps the family of all vector bundles. So this is a one-to-one correspondence here. What we do, this correspondence is from right to left. So if we have a map F of the base to G infinity K, then to this map we assign the pullback bundle over gamma infinity. Okay. So I had intended to give you a fairly good idea of the proof, but as it is, I'm already way over time. Nevertheless, I want to give you the general outline of the proof, because the formal proof is very long and complicated, and it's very difficult to understand what's really going on. But let me explain in intuitive language how this one-to-one correspondence is constructed. So what do we have? We have the set in Rn, and it's very, very large. Well, in the limits it's infinite, but let's suppose it's very, very large. And this is our bundle. So this is a K L. L is a plane, a K-dimensional plane in Rn. And this plane is supplied with a marked point. And this is mapped to, so this here is E and K, and we're mapping it to G and K down here. So in Euclidean space, you have, so this is Euclidean space with these planes. Okay. Now we're given a map of the base. Here is the base, some space, paracompact. Two are Grassmann manifold, infinite Grassmann manifold. And we must construct a bundle over that. Well, we'll do it in the following way. We take some point B of B, and we look. We look at what plane, to what plane it goes. So this point B, suppose it went to this plane that I've drawn here. Now the next step, this is F here. And the next step is this. I'm going to take a copy of B and embed B in R capital N. Now this can't always be done. This embedded B I will denote by B. But if this is a finite dimensional manifold, or if B is a finite simplicial complex, or if B is a finite CW space, it can be embedded in Rn for a sufficiently large n. So I do that, I embed it. Now I do the following. Over the point B, I have B tilde. B tilde is the, I have a bijection here between B and B tilde, and little b tilde is the point corresponding to B. So to that point, I will place, at that point, I will place a plane parallel to this plane here, to the plane which is assigned to B by the map F. I do this for every point B. So I have constructed a map which I call which is the full pullback of gamma and K. And I have an obvious map here. And so what I obtain is a morphism of vector bundles. And it remains to prove that this morphism is an isomorphism. This is indeed the case, but there are lots of things that must be proved to do this. we must prove, first of all, that what I have constructed is really a vector bundle. In the general case, in particular, I have assumed that B is, for this construction, I have assumed that B is finite dimensional, but the construction can be generalized to any paracompact space. I will not say how. So the first thing you want to prove that this is indeed a k-dimensional bundle. I have to obtain a k-dimensional. The second thing that we have to prove is that this bundle is isomorphic to the pullback bundle. And to do that, I have to prove that this diagram gives an isomorphism. To be more precise, that it is, first of all, well defined, because F is chosen up to homotopy. I have to prove that if I take a different homotopic to FG, then I will also get get the same bundle. Also, I must prove that this is injective, and also prove that this is surjective. The proof of surjectivity is a kind of Gauss map, but involves a beautiful trick, which I will just write out here. So I will write R infinity as the direct sum of R even plus R odd, where this is the space of all coordinates with even numbers, and this is the space of all coordinates with odd numbers. And there's a kind of tricky way of shuffling things around between these two spaces to obtain what we have. So you can read this in the booklet. There's a fairly decent exposition in the booklet, but it's not far from complete. If you ever want to read a formal correct proof, there's only one good reference, and that is Dale Posemuller, and it's called Fiber Bundles. And that's all I'm going to tell you in this lecture. I would like to apologize for the way that we have conducted the last few lectures and exercises. In particular, I'm very unhappy of the way that I did my own lectures. I have not succeeded in getting used to the situation where you have to write on a small whiteboard lots of formulas so that the people watching you can read what's written on the. Also, I apologize for taking 25 extra minutes of your time for this lecture, but I really wanted to explain this situation here, which is very difficult to understand unless you have this geometric picture in your mind. So I wish you good luck for the exam. probably the exam will take place on a week from now. I don't know at what time. We'll decide on this later, and I will probably write to you to agree on a time which is suitable for everyone. The style of the exam will be similar to the midterm exam. So there'll be questions and problems. The day after tomorrow, I will send you an email which will contain a list of things that you should be able to do to succeed in the exam. And we'll probably also write a few comments about how the exam will be conducted. So once again, good luck, and I'll be in touch with you soon. Goodbye.
Thank you. Bye.